why don't we go ahead and get started? So I'd like to welcome our second invited speaker, Christina Ilvento. So Christina is a fifth-year PhD student at Harvard. She does research in algorithmic fairness and privacy. And recently she's been doing quite a bit of work related to kind of implementing core differentially private algorithms like the exponential mechanism, the sparse vector technique, in a way that's secure. And this is, of course, very timely work, given the growth in open source projects like OpenDP, which we heard about this morning. So we thought it would be great to hear about her adventures with floating point computation and the great work she's been doing. So with that, Christina, please take it away.
Thank you so much for the introduction. I'm just going to get the screen share started. Can everyone see my screen?
Yep.
Okay, great. So first I want to say thank you so much to the organizers for inviting me to speak. It's really a pleasure to be here talking with all of you. And today I want to talk about some of my recent work, as Michael mentioned, in implementing differentially private mechanisms and some of the things that I've been thinking about to try to sleep a little bit better at night. So I suspect that many of us have either given or attended a talk about differential privacy that's aimed at a general CS audience. And at this point, we're almost like contractually obligated to include some variation on the following two slides. So first, we explain to our audience that anonymization doesn't work. Maybe we talk about practical examples like the Netflix challenge, or we show a differencing attack. But we explain to them that anonymization isn't going to work. But then we say, don't worry, differential privacy is here to help. And we talk to them about our favorite two letters, E and epsilon. And we explain that differential privacy gives very strong guarantees without making assumptions about the computational power of our adversary. And we talk about the important properties of differential privacy, like robustness to side information and post-processing, and supporting composition. And really, when you think about it, these two slides make an excellent start to our pitch for differential privacy, right? You have a problem, and we have a provably safe solution for many of the statistics that you care about. All you have to do is go implement it, go write the code. But this is where the cracks maybe start to appear a little bit in our pitch, because it's not actually possible to translate most of the mechanisms that we write in our papers one-to-one to the code, for the simple reason that we can't compute e to the x exactly with a finite number of bits. And beyond that, even basic arithmetic operations like addition and floating point aren't guaranteed to be the same as their counterparts over the real numbers. And we do know that this can be exploited, in particular when the results of inexact computations are released directly, like in the attacks on the Laplace mechanism of Mironov 2012. But at this point, there is still kind of a question of how worried should we be in general, right? Like if we aren't actually releasing directly the results of floating point computations, like in things like exponential mechanism, or even sparse vector technique, where we're just releasing a string of yeses and nos, shouldn't we be able to reason about these approximations as like a small implementation delta? Like, is this that serious? And furthermore, if I trust my analyst, like they're not trying to exploit weaknesses in my system, they're just trying to do their jobs. Like, can floating point really hurt us? So in the first part of this talk, I hope to convince you that inexact implementations can have serious vulnerabilities that we can't just tuck into a small implementation delta. And this may be sort of surprising, particularly when we're not revealing the results of these floating point computations, because when we think about the error in floating point, we're usually thinking about like error on the order of this XKCD cartoon, where we're talking about like 19.9990 more nines versus 20, rather than like relatively large magnitude errors. Okay, and so to demonstrate these problems today, I want to use the sparse vector technique as our running example. And the reason I like this example is that we'll see that even when we're restricting ourselves to a very simple outcome space of just string of yes and no answers, we can still run into significant problems due to inexact implementation. So I suspect that pretty much everyone here has seen sparse vector technique, but if it's been a while, or if you haven't seen it before, I want to briefly recap like how this works. So sparse vector technique takes in a stream of, well, first it takes in a private database, right? And it also takes in a stream of queries, which we're going to say are all bounded, have bounded sensitivity delta, and a threshold. And what it does is it adds noise to this threshold. So we draw some value rho from Laplace distribution and add it to our threshold. And as each query comes in, we draw fresh noise, add it to the query, and compare the noisy query to the noisy threshold. And if the noisy query exceeds the noisy threshold, we output yes, like yes, this query was above the threshold or top. And if not, we output no or bot. And we limit ourselves to at most C yes answers. So we don't get to answer like arbitrarily many yeses, but we do get to answer arbitrarily many no's potentially. Okay, and so what's the intuition for the privacy proof here? Well, what we're going to do is we're going to demonstrate that the mechanism when we give randomness H, so this set of random variables rho and nu I for the database D, is going to output the same values as the mechanism given randomness, a set of random variables H prime. So we'll talk about rho prime and nu I prime for an adjacent database D prime. And in particular, we're going to pick the following alignment for our random variables. We'll take rho prime equal to rho plus delta. And so we're going to slightly increase the noisy threshold. And we'll take nu I prime equal to nu I if the output was no. So we won't increase the value of the noisy query. So it certainly won't exceed the new threshold. But if the answer was yes, we're going to add the difference in the query values plus delta to nu I prime. And so now that we've shown that we have these other random variables that will produce the same outputs on the adjacent database, to argue privacy, what we're going to do is say that, well, the probability of observing the set H is very similar to the probability of observing the set H prime, because we're not modifying, we're not modifying all of these random variables, we're just modifying rho and the nu I for the yes queries, and we're not modifying them by too much. Now, of course, in this proof, there is a technicality, right? And that technicality is maximum magnitude. So if I align a value rho to rho plus delta, but rho plus delta is too large to actually be expressed on my system, so I cross the maximum magnitude boundary, then it's not really true that we get this nice ratio in these probabilities, because the probability of observing rho plus delta is of course 0. We can't even write it down. But you might be thinking that we're still in technicality territory here, right? Because the probability of observing an extreme value in a draw from the Laplace mechanism is very small, right? So it seems like this should just be, tucking in a delta territory. Unfortunately, we'll see that it's actually quite straightforward for an adversary to exploit these types of boundary conditions. So let's say that we're the adversary and we want to distinguish a pair of adjacent databases, D1 and D2. What we're going to do is we're going to choose the following query. We're going to repeat just this one query. And the query will be 0 for D1 and negative delta for D2, right? We haven't violated any rules here. We're still within the sensitivity bounds. Everything's fine. And we're going to choose a threshold very close to the maximum magnitude boundary. We're going to choose just, an offset of delta over 2 under the maximum magnitude boundary. So what happens when we do this? Well, what happens is for database 1, there is some probability of crossing the threshold, right? We can get a noise draw that's large enough to take us all the way to the maximum magnitude and above this purple line. But for D2, there's no way to cross the threshold. Now, again, you might be thinking, you can distinguish given an extreme value of nu I, but how likely is this to happen? Well, there are two things that are working in the adversary's favor. The first is that they can ask many, many times. Sparse vector only stops once you get a yes. So the adversary can just keep asking until they get their target answer, which is a yes. And the second thing is that your adversary actually, in this case, wants to spend less privacy budget, because the lower the privacy budget, the larger the magnitude of the noise, which of course increases the likelihood of seeing one of these extreme values. And I do want to point out there is a collaboratory notebook, an IPython notebook that goes with this talk that has examples of all of these attacks if you want to go play with them yourself. This one is actually quite practical. Like, you don't have to ask tens of thousands of queries. This is like on the order of, a couple hundred queries to make this work in the examples. Okay, but at this point, you might be thinking, well, I need to be careful about my boundary conditions. I already kind of knew that. But let's have some fun with floating point, right? Because we haven't even really exploited any floating point issues here, just boundary conditions on maximum magnitude. Okay, so if you aren't familiar with floating point, or if you have repressed the memory of what floating point is just a way to represent numbers. And the way that we represent these numbers is a mantissa, little m, times 2 to a signed exponent. And so there are many good things about floating point. I won't get into them, but floating point doesn't behave quite the same way as you would expect when we think about like simple operations like addition and multiplication over real values. So for example, for addition, I can have two floating point values, a and b, which are strictly larger than 0, but when I add them, I get back the larger of the two values, a. So I don't get a plus b back, I get a. And how does this happen? Well, this happens because if I add up two numbers, one which is very large magnitude, right? So this is a pretty large magnitude in our little example here where we have 5 bits of mantissa, and one that's quite small magnitude, right? I have an exponent of +5 and exponent of -5. The problem isn't that we don't know how to add up these two numbers. We're perfectly capable of adding these two numbers. The problem is that when we write down the result, we only get 5 bits of mantissa. So we lose our least significant bits. So okay, it's a little weird, but the order of magnitude of the error is pretty small, right? Because we're chopping off the least significant bits. So in general, this is fine. There are more quirks, of course, with multiplication. So again, I can have two values a and b strictly greater than 0, but I multiply them and I get 0 back. And this happens for essentially the same reason, right? So I multiply two small values, and let's say that my limit on exponents, the smallest exponent I'm allowed to have is -5. It's not that we don't know how to write down the result, and we do know how to write down the result. It's that we don't have a sufficient number of bits in our mantissa or in our exponent to actually express the result. So it gets rounded to 0. Okay, so how can an adversary exploit these issues? Well, the first thing an adversary might do is to just reuse our addition example and turn the noise that we draw to try to enforce privacy into a no-op. So what they're going to do is they're going to choose query values and threshold values that are so large that adding Laplace noise is generally not going to be as large as these values, and the addition is going to turn into a no-op with high probability. So more concretely, we might choose values that look something like this. So we'll choose a query Q, and these values are all printed in hexadecimal. It makes things base 16, so it makes things a little bit more compact. But that's why you're seeing not just zeros and ones here. So we'll pick a query which is approximately 2 to the 56 on database 1, and +1 on database 2. But when we draw our noise, notice that the exponent that we're dealing with here is much, much smaller, right? We're talking about noise with exponent 0 versus values with exponent 56. So what happens is with high probability, when we add this noise to the query, just like we saw on the previous slide, nothing actually happens. We just get back the larger of the two values exactly. So what we can do as the adversary is choose distinct values. So the queries that has distinct values on the two databases that we want to distinguish, but choose them large enough so that the larger of the two values is always matching the threshold, but the smaller of the two is generally not exceeding the threshold, because these noise additions are almost always becoming no-ops. And again, in the corresponding notebook, you can see examples of this. And again, it's pretty straightforward to get this to work. All right, but you might be thinking, this looks really fishy, right? If I'm building a system, I'm not going to just add noise and then be okay with nothing happening after I added the noise. So maybe you're going to add in some checks to make sure that when you add noise, that like something really changed in the value. But the adversary is happy to play that game with you. And what they might do instead is try to build up something that I'll call a sensitivity amplification gadget. So what we're going to do here is we're going to construct a query Q prime that's identical to a safe query Q on paper, but as implemented is going to have higher sensitivity. So what might this look like? Well, we might start with a very boring query Q, which has a value 8 on D1 and 9 on D2. So clearly it has sensitivity 1, very boring, right? These values look kind of reasonable. They're not huge values. They just look like a query you might ask. But then what we're going to do is define a query Q prime, which is just defined in the following way. It's apply Q, add a constant, and subtract that same constant. So on paper, Q prime and Q are identical. But if I choose kind of a fishy constant like this one, what happens is that in practice, in the implementation, they're not identical. And what we'll get is when we apply this to D1, instead of getting back 8, we're going to get back 0 because we have again exploited a no-op addition. But the tricky thing here is that when we apply it to D2, we don't get a no-op addition. And in fact, we get a weird rounding up in our addition instead. And so instead of getting the values 8 and 9 back, we get the values of 0 and 16. So we now have a sensitivity of 16 when we started with a sensitivity of 1, even though these two queries are identical on paper. So this is kind of concerning because we have these reasonable-ish query values. All of the things that are kind of coming out of this interface are in the range of 0 to 16. But we're getting this massive blow up in the sensitivity. And if you're thinking, well, yeah, but that constant looks really fishy, don't worry. Again, the adversary is happy to play with you, and we can do similar things with multiplication by smaller constants. Okay, so what might you try to do to get around this? Some things you could try. Well, you could try to look at all of the query function components in advance and try to confirm that they're safe. But we just saw that these very simple data independent linear transforms, like adding and subtracting the same constant or multiplying and then dividing by the same constant, are enough to build these amplification gadgets. You might also try to do very careful boundary condition management. And I would argue you need to be super careful if you do that. And the interesting thing that comes up with boundary condition management is it's not always clear that boundary conditions that make sense for one setting, in particular for Laplace, are going to compose nicely when you want to do things like sparse vector, where you're taking multiple draws from the Laplace mechanism and adding them or comparing them in interesting ways. So it's not clear that you're going to get composition for free. And finally, you might just say, I'm tired of this. This talk is frustrating me, and I'm going to just disallow all of these no-op additions, and I'm going to monitor these arithmetic shenanigans so that when you're trying to do things that amplify sensitivity, I'm just going to stop you. Well, the tricky thing here is that you probably need someone who knows a lot about differential privacy and who knows a lot about software engineering or scientific computing to be able to implement this properly. And you might end up with things that are very system specific. And so I think the challenge here is that what you're trying to do is you're trying to tell the difference between floating point being floating point, where you're going to have inexact arithmetic that does not behave like arithmetic over the reals, and arithmetic shenanigans, where you're exploiting the fact that floating point is floating point to get, behavior that the adversary wants. So telling the difference between these two types of floating point errors is not necessarily trivial. And furthermore, even if you could kind of come up with a way of telling the difference between these, there's a significant question of what to do if you identify arithmetic shenanigans. Should you throw an error, or has that just now created an error side channel for your adversary? So it's not completely clear how to solve this with these types of defenses in a way that's going to work nicely in many cases. Now, you might say, okay, this seems a little tricky, but this doesn't really apply to me because I am not a crazy person, and I am not going to put my sensitive database up on the internet with just a differentially private interface to it and let anyone come along and just whack it with whatever queries they want to try. I'm going to have a well-defined relationship with my analyst. Maybe they're going to sign a contract with me. I know who they are. And my environment is just much more controlled than what it seems like is being described here. But I want to challenge that assumption just a little bit. And really point out that because the analyst's goal may exactly align with identifying individuals. So if you are doing advertising, it may be the case that new parents or people who are currently pregnant are extremely valuable as a customer base. So your goal to serve ads properly may be exactly to identify these individuals. And it's not totally out of the question to think that we might end up optimizing our way into an exploit, right? Because reducing sensitivity is going to give us higher accuracy for the budget that we're spending. And we, in some sense, have an implicit preference for queries or hyperparameters that exploit inexact arithmetic. So one thing you might imagine doing is if you did some kind of grid search over hyperparameters, and even if you selected among those hyperparameters in a differentially private way, the hyperparameters that correspond to an exploit, like if there's maybe some region where you're accidentally exploiting something, they're going to perform well. So you may end up kind of unintentionally learning your way into either explicitly choosing parameters that exploit things, or just kind of like general practice bad habits that tend to exploit more inexact arithmetic than you would think you're doing. And right, we just told the analyst this is a differentially private interface, everything is safe, so they're not going to necessarily self-regulate out of this. Okay, so hopefully at this point, you're at least sort of convinced that it's worth considering how to get around these types of inexact arithmetic errors. And in the second part of this talk, I want to discuss some of the work that I've been doing about implementing differentially private mechanisms exactly, using the fact that 2 is your computer's favorite number. Okay, so to start off, we're going to change the way that we look at differential privacy. So we usually think of differential privacy in terms of e to the epsilon. Instead, we're going to think of it in terms of 2 to the eta. And this is entirely a mental exercise. It is the exact same definition. It's just that if we use 2 to the eta, we have some hope that we might be able to implement things exactly. And when we move towards implementing things exactly, we remove the potential for exploits based on inexact arithmetic, and we get out of the business of trying to distinguish between like floating point being floating point and your adversary exploiting floating point. Now, there are a couple of building blocks we're going to need to actually make this work. The first is exact arithmetic enforcement, right? We need to actually choose a library that's going to make it easy for us to perform high precision or arbitrary precision arithmetic, and check and enforce that those arithmetic operations are exact, that we're really getting the arithmetic that we expect, not any weirdness going on with floating point. The second thing is we're going to make smart parameter choices. We're going to choose eta in a way that it's actually easy to compute 2 to the eta. This specific set of choices is not terribly important. It's just important that we do this. And then the next ingredient is normalized sampling without division. And this might seem like sort of a departure from sparse vector, but the reason that this is, we're going to use this a lot, and this is an important building block because what we want to be able to do is, given a set of outcomes and weights, we want to be able to sample an outcome with weight proportional to its normalized weight. And we'll see that this is very useful for sampling. And we want to be able to do this exactly. So that's the key thing. We don't want any approximation in this sampling. Okay. And then the next thing we want is we want some nice closed forms for infinite sums. And the way we'll do that is we'll make, again, good parameter choices for eta and a granularity parameter gamma. And so what this is going to allow us to do is, our friend normalized sample has come back. When we want to think about drawing samples from something like a discrete Laplace distribution, I want to be able to make it easy to decide whether a draw from this distribution is greater than or equal to 0. And the way that we'll do that is by making sure that we write these sums in a way that the closed forms are nice and easy to compute exactly. And finally, the last ingredient, which I guess is technically optional, is that we want to predetermine our working precision. And to do that, we're going to enforce bounds to allow us to pre-compute how much precision we actually need to do all of these operations exactly. You do, of course, have the option to not do this if you're willing to, run the mechanism, and if you observe any inexact arithmetic, increase the precision and try again. This, of course, comes at the cost of a significant and very easy to exploit timing channel. Okay, so with those building blocks in place, let's talk about strategy for sparse vector. So the first thing that we're going to do is we're going to switch to discrete base 2 random variables. And the next thing we're going to do is show that we can simulate the behavior of these random variables. And so just because we switch to discrete base 2 random variables doesn't mean that we can actually write down these random variables, right? Like I could still draw an infinitely large random variable that's discrete in base 2. So what we're going to do in the kind of second step here is make sure that we've reduced the effective outcome spaces. So we're never going to look at arbitrarily large values. We're going to make sure that the way that we actually post-process these random variables means we only have to look at values we know how to deal with. And the way that we're going to sample them, I'm calling lazy sampling, is going to allow us to actually clearly simulate the behavior of these random variables without actually having to draw them directly. Okay, and then once we've done that, we're just going to use standard proof techniques to show differential privacy using those original discrete base 2 random variables. Okay, so the first technique I want to talk about is lazy sampling. So the key intuition here is that once we know the threshold, so if someone has already told us what rho is, so we know the threshold t plus rho, we don't actually need to know what nu I is. We don't actually have to draw that value. We just need to know if the query plus nu I exceeds the threshold. So instead of sampling nu I at all, we're just going to sample whether or not the discrete Laplace random variable actually exceeds this threshold. So we would compute these weights for below and weights for above, which we can do exactly. And then we just use, again, our buddy normalized sampling to decide which side of the threshold were we on. So we never have to actually look at the value of nu I at all. Okay, the next thing we'll do is we're going to adjust effective outcome spaces. And this is in particular for rho. So we just assumed that we had a value of rho, but how will we get our hands on that? So what we're going to do is we're going to restrict rho to a finite outcome space and then use lazy sampling again. So everything below our outcome space, we're going to just clamp to the bottoms. This is clamped discrete Laplace. And everything above, we're going to clamp to the top. And again, we can write out these sums very nicely. And everything in the middle gets to kind of enter on its own with its own distinct weight. So once again, we write down some sums that we know how to write and compute exactly. And then we used normalized sampling to actually decide what the value of this, what the clamped value of rho is going to be without ever having to look at the original unclamped value of rho. Okay, so when we put this all together, what we're going to do is we're not going to try to sample rho directly. We're going to only look at the clamped version of it. And then we're not even going to sample nu I at all. We're just going to use lazy threshold to decide which side we're on. And to prove privacy, we're going to again propose and verify an alignment like we did before. And we'll actually choose an alignment that looks very similar to what we had before. So we'll take rho prime, again, equal to rho plus delta. The only difference here being that we're going to have to be a little bit careful in our accounting rather than just adding delta, of adding the actual difference in the threshold that's effective once we clamp it. And the interesting thing about this is that before we had this technicality in this problem where aligning rho prime to rho plus delta was bad because we could cross over this maximum magnitude. We've gotten out of that business because it's perfectly fine to do this for rho because we're only ever looking at rho hat. So this is kind of like nice from a proof convenience perspective, that we've written this in a way that we don't have to change the proof a ton. We just have to be a little bit thoughtful about how we choose to clamp things and making sure that we account for that in the alignment. Okay, so just to recap, what was our strategy? So our strategy was to switch to discrete base 2 noise. We reduced the effective outcome spaces and used lazy sampling to simulate instead of actually trying to draw these values directly. And then we applied standard proof techniques. And really, there's nothing that restricts this to sparse vector. We can do sparse vector with gap using a conditional lazy threshold. We can do private selection from private candidates, exponential mechanism, advanced use cases of exponential mechanism. Really, I hope that this comes across as a more general philosophy. But what we want to do is write what we want to implement. Because this will allow us to translate mechanisms one-to-one from our paper algorithm to the code. And then we enforce exact arithmetic to make sure we really did what we thought we were doing using standard open source libraries. And some of the benefits of this philosophy, at least as I see them, are that we get to relax a little bit about composition, right? If we're confident each of our components is really working in the way it was specified, that there's no kind of weird boundary conditions or edge cases waiting to bite us, we don't have to worry so much about composing different pieces together and whether the boundary conditions conflict. This also can clarify some of the requirements to implement things safely up front, like do you actually need a bound on your query values or do you not? And can also help clarify some timing channels. So a quick reality check here, of course, is like, okay, but like how hard is it to actually do this? So I have a reference implementation of sparse vector and also exponential mechanism and advanced exponential mechanism on GitHub, written in Rust. And this uses MPFR for the arithmetic. And the nice thing is that this is a standard open source library, and it does include these nice, easy to use flags for inexact arithmetic operations, which is very helpful for debugging and actually writing the code in the first place, in addition to kind of having the safety blanket at runtime. But I do want to point out that this is, there are significant caveats that come with this implementation, in particular timing channels, and there's been limited code and proof review, although I do want to take this moment to say a big thank you to Victor Balser and Salil Vadan, who have been helping to review matching up the pseudocode to the proofs to the code to make sure that that all really is doing what we think it's doing. And also Christian Covington and Michael Shoemate, who have provided really helpful feedback on getting this code in better shape to work better with OpenDP. Okay. So there are still some a lot of open questions, and I just wanted to highlight a couple that I think are interesting. So what we've described so far is trying to take things that we're going to write in exactly the way we're going to implement. But we may still have some implementation delta, even if it doesn't come from that translation step, right? Like if you have little Bobby tables in your database and something else can cause crashes in between adjacent databases at different rates, you might still feel that there is some kind of delta that goes along with implementing things between the paper and the code. And so what's appropriate here and how should we quantify that? Second, I want to highlight that timing channels, I think, are underappreciated, and I think they're also not just a problem for adversaries. So one example of this might be that you have an analyst who wants to figure out if e-cigarettes actually help people quit smoking. And so the first query that they're going to run is some smoking rates broken down by age and location, and maybe they see some trend here, the difference between adults and teens. But let's say that they start this query and then they go to lunch, and if the query is done by the end of lunch, then they look at it and take the result. But if not, then they'll try a simpler query that they think is going to run faster. So the problem here, of course, is that if you have a timing channel in between these two adjacent databases, and database one answers this query really quickly, and database two, even though it's adjacent, answers it very slowly, you can have an analyst who, just because they're impatient, is getting totally different outcomes and totally different interpretations of these outcomes because of the influence of that timing channel. Obviously, this isn't differential privacy specific, like this can happen for other reasons, but I think it's something important that we should consider if differential privacy is adding more opportunities for potentially even juicier timing channels. And then finally, there are many other ways that you could try to solve these problems. And a lot of open questions around how difficult is it really to take something that we've written down in a paper and make sure that the implementation, to the best extent possible, really is purely DP, and what costs come along with the realities of implementation. So I hope that this lovely orange box will sometime soon contain your brilliant ideas, because I think there's a lot of different ways to approach these questions. This is just one approach and the way that I've been thinking about it. So before I wrap up, I want to quickly highlight some related works. I will have a copy of this slide at the poster session in case this is too fast to get all of this goodness. And finally, I just want to say thank you once again. It has been great talking with all of you, and I hope that you will all put on your aprons and get out your tongs and ask a bunch of questions. So with that, I will wrap up. Thank you again.
Great, thank you, Christina. That's a great talk. It looks like we already have people raising their hand for a question, so that's great. Damien, you have a question.
Hi. Fantastic talk. Thank you so much for this work and the talk. The examples you gave of safe implementations are, selection type things, or where the outputs are very simple and the shape of the data initially doesn't really matter. In practice, if you have a database that's full of floating point numbers, and you want to compute, let's say, an average or something, it's very simple like this. How translatable is this approach to these type of things where like the input itself is kind of problematic in a way?
Right. So this is an excellent question. And I think this starts getting at the open question of like what counts as implementation delta. But this one, maybe the example you gave about I have a set of floating point numbers and I want to compute their mean. Maybe we can see something a little bit more helpful about that. So one way to think about this is if you calculate your sensitivity with respect to having translated these numbers to floating point, then in some sense you're okay. If you've started out saying, look, the sensitivity is not exactly what you might have thought it was, because I know I've done some rounding in potentially weird ways before I even got to this point, you might be able to reason about that and not actually run into too much trouble. I think where things get more interesting is when you want to do more kind of complicated operations on your data set that maybe are not nice to express with exact arithmetic. Or like it would be a real pain to rewrite whatever your linear regression thing is to use these kinds of semantics. So I think this is an excellent question, and I don't have a great answer for you for how you can exactly use what I've already started with, but I hope someone else is inspired to maybe work on this as well.
Other questions, please. Oh, yeah, Salil, you have a question.
Yeah, fantastic talk, Christina. So first, maybe on Damien's question, I wonder if a potential solution is just before it even goes into your DP, at the very first step, you cast all floating point numbers as fixed point, or the numbers that are represented the way you want to use them in base 2 at the very first step before doing any arithmetic on them. But one thing that was new, like completely new idea that is in your talk that really intrigued me was this idea that these vulnerabilities might be inadvertently found by optimization over hyperparameters, which is a frightening thought. And I thought you're supposed to sleep better at night, but
they make pills for that, Salil.
What's that?
They make pills for that, Salil.
Is there? Have you done any experiments with that? Like any natural context in which you see that actually arising, or ideas if someone wants to explore that possibility?
Right. So I want to be clear. I don't have like an example of this where like here's some system and it's totally broken if you try to optimize your parameters. So in that sense, you can sleep just fine. So I actually think what's much more likely to end up being exploited here is the type of issue that Damien mentioned, where like your input data somewhere in between, like you took your things in Celsius and you changed them to Fahrenheit, and the way that you changed them to Fahrenheit resulted in like some stuff getting squashed and other stuff sticking around. That those sorts of things where like your analyst has, might try many strategies before they actually get to doing any queries, that like, if you think about it, naturally the things that increase sensitivity inadvertently will be the things that survive and will be the things that people remember as performing well. So I think that zero rounding is more likely to end up being exploited inadvertently than necessarily coming up with a gadget. That being said, it is very easy to come up with gadgets. So just like adding and subtracting the same constant, which seems really silly, except when you think about like adding up computations over every row, that if row I has the same value computed as row I plus 1, you have just now like potentially added and subtracted the same constant. So these things are, it's not totally out of the realm of possibility that you would end up doing this. And I think what's more so the examples that I gave here were like, I picked big numbers because big numbers look nice in hex. and they're simple to look at. I think it's much more likely you're going to end up with small numbers being the problem, where you multiply by very small constants and you nuke all of the least significant bits, which will turn some things into zeros and leave other things not zero. And then when you later convert those into values that look more reasonable, like percentages, then you'll get these massive differences. So that's not very helpful, but I do think that this is very much worth looking into. And if you have ideas, I would love to hear about them. If I can help in any way with people who want to exploit this more practically, not exploit this, but like demonstrate more practically what can go wrong, I'm happy to do that.
Thanks, Christina.
Other questions? Well, I guess I'll ask a question. So there was actually a talk earlier at CCS, one of the keynote talks by Alex Stamos, I think. It was a security talk, and it was about sort of like the hierarchy of security concerns, and just sort of writ large. And I think, you know, the idea was that some security issues are things that researchers spend a lot of time on, but they end up like not really causing that much harm. And I think like 0-day attacks were like one that he sort of put in that category. But I just wonder, you know, you've been thinking about sort of different ways that things can go wrong. Are there, and you know, you've mentioned here sort of floating point issues, and you also mentioned kind of timing channels. I guess I wonder, are there other things you're thinking about of ways that things can go wrong with differential privacy, and any thoughts on sort of like how you might kind of organize those into a hierarchy of like which ones are most likely to be really painful and actually cause harm, and other ones that could in principle but may not happen in practice, kind of thing?
Right, that's a great question. And that was a really excellent talk at CCS. I don't know if they recorded it. I hope they did. So like I guess what I took away from that talk is like, there are exploits that like make for sexy papers, and there are exploits that actually really bite us in practice. And I think that that's an important point. And so Michael mentioned a couple of the issues that I'm concerned about. So timing channels for sure. I think timing channels are more likely to turn into the not quite statistically valid type of problems rather than, I mean, certainly they can also be exploited. And then floating point, I'm much more concerned about. So I think the real question in my mind when I think about floating point attacks is certainly an adversary can exploit them. So I encourage you to go play with a Colab notebook and try to convince yourself otherwise. But I think more than an adversary can exploit them, I think one news story of an adversary exploiting them, when you go to make that pitch of like, look what your adversary could do with a differencing attack. And they say, yeah, but like, look what your adversary can do with this implementation of differential privacy. How are these two things different? That in some sense, it takes a little bit of the teeth out of why we push so hard on like not just using anonymization and saying like, oh, well, okay, like good enough. So I think in some sense, we have to do a little bit of practice what we preach there, or there's the kind of potential for like PR and pitch problems, whether or not they end up being like exploited all the time, all over the place. To me, I think also there's a question of like, how difficult is it to prevent like all 0-day memory bugs versus taking some steps to try to write algorithms in the papers in the way that we're going to write them in the code, and having like some level of, we're going to try to be disciplined about this, but maybe we're just going to document timing channels and we're not going to actually worry about squashing every single timing channel. So I think in some sense, in my mind, there's also kind of like a difference in difficulty level of like squashing all memory bugs versus trying to like change a little bit of mindset. Other than timing channels and floating point, I think crashing bugs are probably, there's something I didn't talk about really at all here, but like error side channels and I can make your system crash side channels may also be something that end up getting exploited or end up being something that stop people from using certain techniques that, you know, basically, again, we're like, I don't try to use these hyperparameters because they cause a crash and end up using something else. which again may be more in like breaking statistical validity territory rather than like breaking privacy territory. Hopefully that's helpful.